This is the BhamQuants presentation on December 4th, 2019 for data modeling for business applications.
All right, well, appreciate everybody joining us and the opportunity to sponsor this meetup tonight. So I'm Josh Jones, and I'm the CEO of StrategyWise, and just wanted to really kind of introduce our company and sort of warm it up for Peter. We originally were debating on whether we were going to do 2 talks or not, or just one. It sounds like we're just going to do one. I'm going to let Peter talk about his projects, and I think you guys are really going to enjoy that. It's pretty fascinating what we're doing over there. Before Peter jumps in, I just wanted to tell you briefly about StrategyWise as an organization, and just hit on a couple of quick points, really more of a thesis of how we operate as an organization. If I can get the slides working here. There we go. So our mission is to help people use data to thrive, and I'll just speak to this very briefly. Through the years, so we've been a data science and AI consulting firm for about 6 years now, and one of the most common challenges we found in this space is that because it's really exciting, some of the shiny new toys, if you will, some of the cool tools, like right now everyone's talking about artificial intelligence in the market. It's very easy to get distracted by that and forget real business case. And so a lot of what we really try and focus on is when we work with a particular client is how are they going to be successful in their job, in their career, their division, or whatever it is. And then ultimately, how can we help them use data to thrive? And so over and over again, we see data science projects fail for a variety of reasons in organizations. And one of those leading reasons is just lack of a business case. It's a really cool tool. Hey, we can do this. Hey, we have the new capabilities or technical capabilities to do something, but if it doesn't actually drive that business purpose, if it doesn't make that individual or that organization successful, then ultimately it won't have long-term stamina. Because for all of you that have worked on data science projects in corporate environments know it usually takes a lot longer than you expect. There's a lot of R&D in that process, and you need that stamina to continue to invest as you move forward. So again, that's our mission. Very briefly, we work primarily with enterprise clients. So typically for us, we're going to be working with companies in the 250 million in annual revenue or greater. We do a lot of work in Atlanta as well. We have an office over there. We're headquartered here in Birmingham. We do a lot of work with Southern Company, the different utilities. Chick-fil-A is also a larger client in the Atlanta space. Very briefly, before I turn it over to Peter, I'll just talk about 2 different projects that we do, that we work with clients, and happy to talk to you guys offline if you want to know more about these. But the first of these is what we call a data science roadmap, or a data science discovery workshop. And that's essentially where we help companies that have a large amount of data, and they want to figure out how to use that or how to leverage. Maybe they've heard about AI, maybe they've heard about advanced analytics, but don't really know what that means, or maybe they're fledgling, they've hired a couple people, but they're really struggling to figure out, okay, we've got 10 different projects, which ones should we go through? This is really a strategy project where we go through and help them identify organizational impact. We look at things like data quality and accessibility, feasibility of different projects, and so forth. And then the other one, I felt like this might be interesting just to talk about for a couple of moments, and this is our data science process that we use as an internal guide at StrategyWise. And so whenever we do a data science project, we try and go through the same process over and over and over again, and we do it in I would say, a mostly agile methodology. And what we do is we start with a business objective. So this is, I want to predict customer churn, or I want to predict, identify driving distance, or some sort of predictive models end goal of how you're changing some sort of business objective, if you will. The next step we move into is in data engineering. So this is where we capture that data. It could be IoT, it could be converting PDF files, it could be running SQL queries on a database. And then as you know, there's a lot of munging, a lot of data hygiene that occurs there. And just as an FYI on the left here, you'll see some of the different products that we use in this process. We're a Microsoft Gold partner, so we tend to lean on their products, but from time to time clients will ask us to do things, whether that's in the AWS environment or some other tool. We'll use those as well. Once we've got the data, we've got it clean, we've got it ready to use, we go into data exploration. And this is where we really start getting those initial insights, things like summary statistics. We start looking at data quality. Do we have enough data to use here? And that's a very iterative process. In our shop, we typically use Python. A lot of the stuff Peter will be talking about today is Python-based. We use Jupyter Notebooks. We also do some R. I'd be curious to hear from you guys that are practitioners, particularly of interest in non-StrategyWise folks. What's the current trend? We were really heavy on R a couple of years ago, and now we sort of veered towards Python. What are some of the tools that you guys prefer?
My company doesn't use anything of the sort. However, everyone that I'm talking to is absolutely 100% on Python.
Mm-hmm.
Exactly what you're saying is R seems to be going on the down. They're becoming less and less popular, but Python basic.
Anybody else?
Yeah, I feel before that I've been talking with, they say the same thing.
Yeah, moving towards Python.
Yeah.
I was fascinated. We were in a enterprise client's office yesterday, and they mentioned they had some models we were putting into deployment, and they mentioned that they had built the models in SAS, and I was sort of bracing for impact of, okay, now we got to deal with SAS for the next year. But thankfully, the data scientists there, very quickly said, "But I would love to move these into Python."
Very quickly.
Yeah, and so they're already paying. She's not paying the license fees for SAS, but they've got it in front of them, and she's saying, "No, I really want to go to Python." So it is interesting to see how that trend is changing in the industry. So once we've done the data exploration, we know what we're working with. That's when we start building those models, and we usually do our first round of predictive modeling. We always really caveat with the clients, when we come back to you with our initial round of models, it's exactly that. It's an initial round of models. We're almost sure we will have missed something because it really is a conversation. No one knows your data like you do. So it's usually, we're going to bring you a first draft and figure out what we need to go back and tweak, make some changes to. And so there's that iterative process of building those models. And then we move those models into production. This is something that I think in the early days of data science, a lot of people really just thought about models as sort of the end goal of data science is to build some sort of algorithm or some sort of formula. But more often than not, you need some way to put that into production, to deal with things like data creep, to deal with just the changing landscape, changing environment. So when we talk about machine learning, retraining models, or putting these into a large deployment environment, there's really a whole new set of skills that are involved there. And a lot of times the companies that we've worked with, that's relatively new information. And so there's a challenge in thinking through, well, wait a minute, I just paid you to build a model. What do you mean now you have to do this thing called deployment or production? But if you really want to be able to use these things in an enterprise environment, as you guys I'm sure know, that's an entirely different set of skills. And so that's something that we help them through as well. And then finally, in the implementation and training stage, this is really whether that's putting something into Power BI dashboards, whether that's building APIs. In some cases, that's change management. A lot of times the algorithms that we create, the end result is us saying, well, you need to change this business process. You've been doing it this way. You need to change it and go back and do it this way. And a lot of times between each one of these stages in the wheel, we'll find that we have to stop, wait for the client, some sort of business case to go through. We don't really push things like production, for example. We'll rarely actually quote out the cost or the time of doing something like deployment until we've actually done the model to make sure that we've got something to work with. There's no reason to build this thing all the way out to the end if you go to the model and find out where there's actually no signal. We've just wasted a lot of time. So there is some iterative process in that. And then finally, as we, and I'll say implementation and training in many cases can be just as critical as any parts of the technical process. You can build the world's best predictive model, but if you have boots on the ground rejected or sabotaging the project or afraid that AI is going to take their job, your project is going to fall completely flat on its face. And just in the last week or two, we had a client where we presented something, we're like, this is going to revolutionize your industry. And I could tell the people in the room were getting very uncomfortable because what we were saying essentially is, this could do your job for you. And so obviously there's some political conversations that need to be had there as well. But then as you go through all of this process, that's when we recommend master data management and data governance. Again, this is a practice in and of itself as well. It's something we normally don't lead with in the sense that everyone's got more data than they know what to do with, and typically they're going to have more data than they can use. And so it's very inefficient, and it's a waste of time, emotion, and energy to go in and just manage data for the sake of managing data. But if you've actually built a business case, and you said this is how this is going to impact our business, and savings or strategic value or something like that, and you've built models that are showing signal, and now you've pushed them into production, typically it really is part of this production, this final implementation process. Chances are in stages 2 and 3, the data scientist has done a lot of cleaning to get that data ready, but before you can release that project into the wild, if you will, you have to put governance processes in place so that new data that's coming in the pipe isn't going to break your whole system. So this is really the data science process at StrategyWise. I wanted to share this with you guys just to give you kind of a peek under the hood in terms of how we practice data science when we work with clients. And this may give you a little bit of backdrop into when you think about projects like the work that Peter's going to be talking about today. This really was just a quick overview for you. And with that, I'll pass it along to Peter.
Thank you, Josh. Oh, hang on, Mike.
Yep. And I'll let you switch over your PowerPoint here.
No worries. Okay. So thank you, everyone, and thank you, BhamQuants, for having us. Okay, my name is Peter Rosenmai. As was mentioned, I'm a data scientist at StrategyWise. Okay, now I'm going to be presenting tips here about simulation of business processes. Okay. Now I'm going to try to make the slides not too word rich, so I'll make it fairly lean and I'll just talk to the slides. Okay. So, what is computer-based simulation? I suspect most of us know what it is, but let's just say sorry, I'll see if I can get this working. Just one second. There you go. Let's just say it's using computers to emulate dynamic processes. Okay. So what you see here is an example. It's from an animation we've done of which is actually produced by one of our simulations. You see cars entering a drive-through. At the moment they're coloured grey because we're in the warm-up period for the simulation. In a moment you'll see them become changing colours. You'll see them go red when they're in this lane here, which is the ordering section, because they have tasks to do before they can leave that section. They have to have one of these ordering people here, one of the dots, come up to them and take their order. Okay. Now the payment time, the time it takes for someone to take their order, or to take a credit card order, or to take a cash payment. These are all determined by distributions which you specify when you set this up. There's basically a spreadsheet which describes each and every simulation, and my code just runs through the spreadsheet, running whatever simulations you've specified there with the distributions that you specify. Now, once an order, there we go. We're now in the actual run period. Cars are changing colours. Now, once an order is taken, it goes to the kitchen. Cooking goes on in the kitchen. Cars go through the payment section, which is payments are currently not being taken in the payment section; they're being taken in ordering. And over here, the kitchen counts down. Food gets ready, gets delivered to the cars, and off the cars go. This is something we call a pull-away lane. If this car here is jamming everything up, and this car here is ready to go, it's got its meal, it goes off by the pull-away lane. Okay. Now, there's a fair bit going on here visually. If you know how to interpret it, it all makes sense. Like the various dots, the various colours, even the stripes on the cars, they all mean different things. And I actually need to have this because it helps me analyse to see what's going on. This whole thing is actually very dynamic. So just by changing, a few cells in a spreadsheet, I can make it say 3 lanes, or if I wanted to, 10 lanes. I can take this away, this pull away section away. I can add parking. I can add more attendants. I can describe how the attendants move somewhat. I can say where the attendants can get to, what gets done in each section of the drive-through. Taking orders, taking cash payments, taking card payments, delivering food, etc., etc. There's quite a lot that can be done, and of course the distributions that govern how long every task takes. Why would you do something like this? Well, you want to speed up a drive-through, basically. You want to find a way of getting more cars through and getting cars being in line for a lot less time, or at least having their food in their laps sooner. Okay, now I'm going to talk about the advantages of simulation before I move on to the tips. Now, let me just try to change slides here, 1 second. Okay, now I suspect some of us have encountered this before. Simulation is really great for dealing with mathematically difficult problems. So, as an example, suppose you're trying to simulate transactions. Now, you suspect that transactions, the number of items in a transaction are governed by, say, a Poisson distribution, okay? And you suspect that the time it takes to process each item in a transaction can be given, say, by a log normal distribution, all right? Now, how long does it take then to process a transaction? Well, that's the sum of these of samples from a log normal distribution, right? Now, if you ask me to go away and work out on paper, what does that distribution look like? It's going to be difficult. I'm going to have to get out my maths books. But you can literally, in like seconds, it might take you a couple of minutes to write it, but you can get some code. You can do say 1 million samples, and you can quickly produce the distribution. Here's me actually doing it. So I'm just going to. I know we said bad things about R, but I still use R. And here's me using R to do this. So you can see I'm taking 100,000 samples. I've got my Poisson distribution for the number of items in a transaction, and a log normal distribution for the time it takes to process each of these items in the transaction. Okay. Want to know what it looks like? Let it churn away for a moment or two, and it'll show me a pretty picture. Okay. Much easier than going and churning through the maths. Just so I know what sort of group I'm dealing with here, who does that sometimes? Who goes into R or a similar program and you want to know what a distribution looks like, so you do something like this. Does this ring a bell for any of you? Yep. Okay. There's the distribution. Yeah, that's a very simple form of simulation. Okay, and as I said, it examples well how simulation is great for dealing with these mathematically difficult problems. Sometimes problems which are pretty much mathematically intractable. Simulation can answer them. Okay. Now, cases where data is lacking, simulation is great for that. You might know, like I just said, you might be able to make some decent guesses about how many items there are in a transaction and how long it takes to process a transaction. You can create your own data set, okay, using simulation. At least you've got something to then work with. So yeah, cases where data is lacking, simulation is great. Experiments. Simulation allows me to run experiments quickly, cheaply, and fast. How could I simulate a drive-through except by using a computer? I mean, I believe I think I've heard that McDonald's has a restaurant entirely for simulating. It's correct, yeah, entirely for simulating different processes. But that's expensive. It takes time. Computer-based simulation is great. For example, you saw with that drive-through the way that we had that pull-away lane section. Using simulation, we saw that a pull-away lane is actually quite an effective thing to add to a drive-through. Okay, this is a good one. Convincing non-analysts. You show them the animation in particular that results from a simulation, and really they're very often good to go. It can be very convincing. Okay, and finally, for explaining complexity. For explaining complex behaviours and also for confirming intuitions. For example, we thought that the pull-away was going to be effective, but when we actually saw the cars moving around the drive-thru and we saw the way that they're interacting, that's what really confirmed it for us. Also, if you've got a bottleneck in a system and you don't know what's causing the bottleneck, simulation can be great for that. You might know where the bottleneck is, but what is causing it? Okay. Now I'm going to move on to the tips, since I've said a little bit about why I think simulation is good. All right. So first tip is consider each simulation process in isolation. Now, a simulation can involve an awful lot of parameters. If you're simulating a restaurant, you might have you have the place where the orders are placed. You've got the kitchen. You've got the delivery of the orders. All these various things. Each of these sections can have quite a few parameters. If you want to really churn through all the possibilities, you're looking at so many possibilities. It's just unmanageable. Okay. So, first tip: look at each section in isolation before you consider the whole. Find out what's going wrong in each section. In particular, what you want to do is you want to find out what the throughput is. So you flood it with demand, and you see what sort of numbers you're getting, how much you're getting through. Okay. So once you've done that, you'll often see something that looks a bit like this. Okay. You might find that you've simulated each section of the restaurant in isolation, and you're getting throughput numbers like this. Okay. Now you're going to see that there's interaction between the various sub-processes in this larger process. For example, if the kitchen is the bottleneck, maybe staff from the ordering section come into the kitchen to help things out. Okay, just as an example. Now, something you do have to watch out for when you look at each section in isolation and then you try to consider the whole is this. You see here that the lowest throughput is 100 customers per hour for the ordering section. What would you guess is the throughput for the overall restaurant? Yeah. Mm-hmm. Generally, I find that that's actually not the case. In this case, because of this number here, 110 for paying, the paying section is almost the bottleneck. So what sometimes happens is, although ordering is generally the bottleneck, there'll be times when the ordering section is going fairly well relative to its normal performance, but the paying section becomes the problem. So when these are close, I noticed that the number will actually be below what the lowest number is. So just watch out for that when you're analysing each section in isolation. Okay. Now my next tip is that you should graph the simulated process, a sub-process and the overall process. Graph the simulated process over time. Now, this is an awfully complicated graph, but this is the sort of thing which I produce in order to understand what's going on in the simulation. Okay. Now, this is going to be useless to a CEO. They don't want to see something like this. But to me, as someone who's coded this up, I really want to look carefully at this to see everything is going on the way that I expect it should. Now, let me just give you an example here. You've got this, the fish fingers platter. You see it's going through different states indicated by the colours, cooking, ready, and so forth. We've got down here the prep areas, and you can see that they're in use, and then they go blue, which means that they're being cleaned. And you see these lines, these vertical lines between these different resources. Those indicate that one resource is claiming another resource. So, for example, a fries platter claims a cooker. There you go. You see what happens there? It claims the cooker, and then at some point later it releases it. Okay. This sort of stuff, as I said, it's for me, and it's also for process engineers who really, I can tell you, they really are interested in this stuff. And up here in these topmost graphs, you've got the number of items. In this case, number of fries in hot holding section, in the assembling section, in the shoot section, and so forth in the kitchen. Okay. Now, just as an aside, if you're doing this really well, the way to do it, I believe, is actually to create this in a browser. So, who here has used D3, for example? Yeah, some experience with D3. Do you all know what it is?
No.
Okay. D3 is a JavaScript language for graphing. It's fantastic. It's the base of a whole lot of other JavaScript languages. And what it gives you is something that you can't get generally just from using R or Python. It gives you interactivity, which is just fantastic when you want to do an analysis like this. You can you put your cursor over something, it gives you information about what you're looking at. You can turn elements on, turn them off. You can order these things in different ways to make it more explicable. In my opinion, a really good data scientist is somebody who can actually put together some sort of a website which can display this sort of thing. So yeah, graphing things at this sort of level, very important. Now, another form of graphing, animation. I think it's essential to include animation in almost any simulation. A trivial one, not so much, but for example, a classic idea of a classic simulation is a phone bank. Okay, somebody calls up, an operator takes the phone call. They might then write something down. They have a break later, and so forth. Even something as simple as that, I would incorporate animation so you can see what's going on, so you can convince the client that the simulation is actually doing what it should be doing. You bring the simulation to them and they say, oh, wait, we didn't incorporate toilet breaks, we didn't incorporate that. They actually start thinking about it properly. And something we've certainly found is that the power of animations to convince people of your results, I can't off the top of my head think of a better way of convincing, especially a non-technical audience, of the veracity of your results than through an animation. Yeah, I can't think of any better way. We've seen that again and again. Okay, now a slot-based approach to animation. This is the way that I think you should be doing your animation. Now, have any of you seen one of these? Donkey Kong? This is from 1982. If you remember, Mario moves. He doesn't move smoothly across the screen. He moves in little jumps. Jump, 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 jump. There's only about on that lower level there might be 5 places where Mario can be. Okay. Same with that top level. So there's specified slots where each of your components in the simulation can be. There's a limited number of them. Now, that's the way I recommend that you do your simulations. I have tried to do simulations. Foolishly, I have tried to do simulations before where you had continuous movement of objects. Has anyone here ever tried to write a computer game? Yeah. Okay. Yeah. So you use sprites, for example. Now, the trouble with doing a continuous animation is you've got some really hairy stuff. You've got some hairy mathematics. For example, if you're trying to accelerate a car through an arc, the maths actually gets quite hairy. You have to pull out your you have to do some calculus. It can be difficult. You also have to worry about deadlocking, where you've got, say, 2 sprites which are you've seen it in computer games sometimes when there's 2 sprites either jam on each other and get deadlocked. You know what I'm talking about? Yeah, you have to watch out for things like that. It's a whole lot easier to write it using this slot-based approach. By the way, if you do decide to not use the slot-based approach, you do want to look up something called blitting, which is a way of speeding up the performance of continuous movement animations. But yeah, use the slot-based approach. One of the reasons why slot-based approach is better is because when you create the animation, what you do is that at the very beginning is you actually draw your sprites in all the sections where they can go, and then you just hide them, okay? And when you come to produce your animation, when you come to produce a screenshot of your animation, you just turn on whichever sprites you want to show, okay? Change the colors of them. Makes things go a lot faster. Just don't do my mistake of trying to do continuous animations. It just doesn't work. Okay. Now, still talking about animations. Generate videos rather than on-the-fly animations. I kind of hope this would be obvious. If you're generating on-the-fly animations, you basically have a window pop up and you see your animation as the code is running. Well, there are problems with that. There are points in your code where the simulation is very processor intensive, where the simulation will really be slowing down and your animation starts to slow down. The best way I've found to do this is, for example, if you're using Python, you'll generate a JSON log file, okay? So you run your code, you run your simulation. Every second or so, there's an event call which basically takes a snapshot of the state of the visual state of your simulation, and it saves it as a JSON file. Okay, or it saves it really as a several lines of JSON. Okay, you all know what JSON is, yeah, right? And what you can then do is, if you don't feel that you're capable of writing the simulation component of the animation component of your simulation, just pass it on to somebody who's able to. You can give the person that JSON file describing at each second what your simulation looks like. Pass them that JSON file and let them do that job, or rather, let their code do that job. Okay, so it separates nicely the simulation from the animation. Okay, and one more tip. In Python, if you're looking to do this, the way to do it really is to use a facility called FFmpeg. It's a free facility which basically takes all your snapshots, your video snapshots, and changes them together into a video. Takes a few lines of code to run, nice and easy. I see, Casey, you...
I've used it, yeah, a little bit when we tried to kind of parse out. We were doing some stuff with our the camera stuff we were looking at, Josh, and we used that to actually split it, so we went the opposite way. But yeah, super easy library to work.
Yeah, still on the comprehensive log files. Still on the log files. Okay, you see here two different types of log files. At the bottom, you see the JSON file that I just mentioned. Each one of these, there's the time, 174 seconds into the animation. That describes exactly how the animation looks at that point in time. So you see, for example, the car with ID 12 is in the restarting state, and it's finished in the road section, so on and so on. Up the top is a more human-readable log file. You can actually see where the runner is in a different section. You can see what they're trying to do. For example, this first car, it's moving forward. It's going to be doing its next action at in about 10 seconds. Okay. Now, as I said, you can pass the JSON file along to your animation software. Now, here's a quick little tip for those of you who use Notepad++. I'm sure you've seen this. I've had to analyze a lot of these files, and it's just very useful to have code highlighting. You highlight something that you're interested in, and it highlights every other instance of it in the log file. It just makes analysis of these log files much easier. It's just such a tiny thing, but it helps a lot. Okay. Now, base your iteration loop on a non-fixed time interval. What does that mean? Now, the most obvious way of doing a simulation probably is you'd say, okay, I got a counter every second. We check to see what's going on in the animation, in the simulation. Is something ready to change states? Is something ready to move? Is something ready to change somewhere in the simulation? If yes, do that, and then go back to the top again. It's basically a for loop or a while loop. Now, that isn't the way that I recommend doing this. I don't think you should have a fixed time interval. There are several reasons for that. I'll come to that, but let's just first of all have a look at an example. This is an example of a simulation not using a fixed time interval. So we've got here an elevator simulation. So we've got an elevator which will reach the first floor in 5.6 seconds. Elevator 2 will reach the first floor in 9.2 seconds. Person 1 reaches the door to elevator 1 on the first floor in 7.1 seconds. And it takes 1.8 seconds to enter a waiting elevator. Okay, so the first loop iteration will be 5.6 seconds. So it's not a fixed amount, it's 5.6 seconds, which is the time it takes for elevator 1 to reach the first floor. The second iteration is 1.5 seconds, the time it takes for person 1 to reach elevator 1, and the next is 1.8 seconds, which is the time it takes for person 1 to enter elevator 1, and so on. Okay? Now, there are several advantages to taking this approach. First of all, it accommodates actions that take less than one time unit. Now, you may think that you don't need to worry about actions that take 0.9 seconds rather than 1 second. What difference does it make? Well, actually, it does make a lot of difference. Suppose you're in a queue. You've got 20 people in front of you in a queue, and the simulation says it takes you 1 second to move forward, whereas in fact, in truth, it takes 0.8 seconds, okay? So you're going to be accumulating error for 20 different movements forward. It can be quite easily happen, and I've seen it, that a simulation with these sort of rounding errors, it can get serious problems, okay? So I strongly recommend that you don't use a fixed time interval counter. And also it speeds up simulation runtimes. When your simulation is on a second by second counter, a lot of the time nothing will be happening in the simulation in a given second. It'll just be idling while you wait for something to get done. So you just jump past that, okay? Now in technical terms, in simulation parlance, what I'm saying is use next event time progression. So that's the name of this sort of simulation, next event time progression. Don't use fixed increment time progression. Okay, now next, object orientation. This does require, simulation requires a fair bit of coding knowledge, and if you've got the knowledge, if you can write a simulation, you should know, just looking at a task like this, that it's tailor-made for object orientation. I mean, each car is obviously an object, each customer is an object. I would dread to write a simulation without using object orientation. It would be horrible. Okay, now the next one is a big one. Try not to hard code the simulation process. All right, now I'm going to be speaking about this one for a little bit longer than some of the other points. So a lot of simulations look remarkably alike. What you'll have is a common pattern like this. An agent, for example, a food tray, it enters a new state, which is, for example, food prep, okay? And the agent stays in that state for a period of time determined by some distribution, okay? Then it moves to the next state. For example, a food tray may move to the frying state, or it waits on a resource, for example, a fryer, before it can move to that state. So a very common pattern. And you see here me basically producing a table showing you how these agents, the fryer's platter, the fish fingers platter, and the fryer, how they could be described in a simulation. So what I'm saying to you is, as much as you can, if you're writing a simulation, don't hard code this sort of process. Have your simulation actually read in a Excel file of some kind which contains the information, which contains the process information. Now, I'm going to show you an example of that sort of file that I've actually used. Let me see if I can find it. Okay, so this is what I've actually used. This is what I've got. I wrote a simulation engine. It basically reads in this file, and it churns through and follows the process described in this file. So, for example, here you see a nuggets pan. It can go through various states. It needs various resources. To go from some states to another state, it needs a worker. So to go to a breading table, it actually needs a worker to take it to the breading table. Over here you see the time it is in each different state. I'm just using a uniform distribution here. Now you see these extra resource requirements. What this is, no simulation engine is going to do exactly what you want. You're going to need to have some bespoke code for every simulation, pretty much. Okay, but the way I find that is best to add that bespoke code is in your process file describing the process. Just write the name of the method in the. Sorry, let me describe this better. You have your class, which is your simulation class. You inherit that class in another class, which is to be the simulation that you actually run. And in that class, you provide these methods, the ones you see here. For example, breading table is ready. That'll be a very short method to check whether or not the breading table resource is ready. Predicted demand exists. Another quick little method. So this is the way that you write the bespoke elements of your simulation. Now, There's more, of course, to this file here. I'll just quickly show you. I've got my various agents, some attributes that they have, their priorities, and some demand and so forth. Now, I have another. This is a cleaner example of the process file for a simulation, and this is worth having a bit of a look at. Okay, so every simulation you need to specify the warm-up time, the run time, how many runs you want to do, and you also want to give them a random seed. Okay. In this case here, I have a first seed. So what that says is the first simulation run uses seed number 1, second simulation run uses seed number 2, and so forth. And if you find that you've got a particular problem with if one of the simulations has funny behavior, you can use that seed to rerun it and see what the problem is. Okay, here are my resources. So I've got pans, workers, fryers, and something called a cleaning cycle. Now, I allow a resource to actually have more than one unit. So, for example, this fryer can be used by 2 different pans at once. And this is a real thing. You have a deep fat fryer. You can use 2 pans at once in many deep fat fryers. Okay. And these are the entry states. These are the entry times. Basically, what I'm saying here is that you've got 1, 2, 3, 4. You've got 4 pans at the start, and you've got 1 worker starting at time 0, 1 fryer starting at time 0, and 1 clean cycle starting at time 0. If I want to have something like orders coming in, what I will do is this. I'll type in something like that. That says that if I have orders coming in, an order can be expected to come in, what is it, every second there's a 1% chance that an order comes in, okay? So this is basically using an exponential distribution to determine the time to the next order. Now, here are my state transitions, saying a pan will go from its start state, which is waiting to be filled, to its next state, which is being filled, and from that state it will go to waiting for the fryer, then it will go to going to fryer, then it will go to frying, then we'll go back to waiting to be filled, okay? And I've got another function here, which is a bespoke function that you need to define in your class that inherits the base class, the base simulation class. I've got my my states here, functions strings describing how long you stay in each state. So, for example, here, a pan, how long does it take for a pan to be filled? You use a log normal distribution with these parameters. And finally, I have my resource requirements. So, when we come to the cleaning cycle needs to grab a resource. The resource it needs to grab is a fryer. When the clean cycle wants to go into the cleaning state, it needs to grab a fryer resource, and it needs to grab 2 units of that fryer resource. In other words, it needs to lock down both of the fry baskets. Okay. How does the clean cycle know that it's time to do a cleaning? It calls this function here. Fryer has done 10 fries since last clean, and in a previous slide here, you might have noticed I increase the number of I increase a variable each time that a pan leaves the fryer. Okay. So yeah, what I'm trying to say here is, please, if you're writing a simulation, try as much as you can to soft code it. It helps enormously. Your code is more robust. It's more extensible. It's all about managing complexity. This is the way to do it. Okay, back to my presentation. Now, the next point, I think you've already seen it. I'm suggesting that you incorporate a warm-up period. I think this should be kind of obvious. If you want to investigate the workings of a drive-through, you're probably going to be interested in how it works at peak hour. Okay, so you don't want to start having your cars go into the drive-through and collecting statistics from the moment they're going in. You want your drive-through to be basically in its most operational state. You want it to be full of cars. So you give it 30 minutes to warm up, to get full of cars, and then you take 60 minutes worth of statistics from that point onwards. There can be some people will argue that if a car comes in the warm-up period, but it exits in the non-warm-up period, you count that, soft code that, and if the client disagrees with you, you can just turn that particular lever on and off. Okay. Poisson processes. Okay, so this was a little bit mathematical.
Before you go there,
Yep.
I'm thinking about your warm-up period, and I dealt with a situation once when they were dealing with staffing for a facility. And so at 8 a.m. sharp, the staffing began, and there was a ramp up, then you get steady state, and then there's a ramp down. And so literally, we had to model that warm-up period and cool-down period. So what I'm hearing you say is to model the steady state, to ignore those warm-up and cool-down, which were critical to us, of course. Do you have advice on how to handle the warm-up and cool-down?
Well, what you could do is, so the way I've been modeling things here is, for example, for a drive-through, we've got a set rate at which cars enter the drive-through. There's no reason why that can't modify over time. So, you know, if you really want to look at entrances between 11 o'clock and say 2 o'clock, and your peak hour is 12 to 1, you might start off with say 11 o'clock you've got 80 cars per hour, and you ramp it up to maybe 200 cars per hour in the peak hour time. There's nothing particularly hard about that. Yeah. Okay. Now I'll just come back on this. Now, the next thing I'm going to be discussing, just very briefly, Poisson processes they're very useful in simulation. There's not a lot you really need to know. I'll just wait for the thing to come on, because I need to show some numbers.
Soft coding. What are you referring to there?
What I mean is the process of your simulation, the way that agents in the simulation change states and the resources that they wait on. Put that information in an Excel file somewhere that gets read in by your code. So it makes it just a lot easier to change your simulation. Okay. Now I'm not going to spend much time on this. On the mathematics here of Poisson distributions. I often hear people when they talk about simulations, they say, oh, we need to use the Poisson distribution for how the cars enter the drive-through, or how customers enter the restaurant or something like that. And often you don't really need to use anything like that. If you've got rare events, if you've got 100 customers coming in an hour, which is what I believe I've got here, 100 customers coming in an hour, the probability using a Poisson process that more than one customer will come in the same second is, what is it? It's just about, it's very small. It's whatever that is. Yeah, just about 1% of times, just over 1% of times, will you have two customers coming in the same second. So don't bother using the Poisson, this sort of stuff here. Just basically to take a sample from a uniform distribution, and if it's less than this number here, you've got a customer coming in, and don't allow two customers to come in the same second. Now that's the case where you're using a fixed interval. This is for a fixed interval simulation. In the better case, where you're using where your interval is not fixed, just use that formula there to give you the time to the next entrance. Okay, I'm sure you've seen this before. It's from survival analysis. The time to the next event where you're using an exponential distribution. But yeah, I use this all the time in simulation. All right. Another little math thing. I've often found when I work with people in their simulations that they love the triangular distribution. People love this. And the triangular distribution is not the best distribution in the world. So I'm suggesting that you think a little bit beyond the triangular distribution. As I'm sure you know, the triangular distribution is defined by a minimum, a maximum, and a mode. The reason why people love it, people like me don't love it, but business executives love it because they can understand it. The parameters are simple, okay? First of all, it's bounded, which is great because it can be troublesome in a distribution when you've got unbounded distributions. They can be really problematic. It allows for asymmetry, and as you all know, business data tends to be asymmetric. Easily parameterized, definitely. However, it's not a reasonable approximation of reality, okay? One of my favorite distributions in simulation is the log normal distribution. It has its own problems, of course. It's unbounded, at least on the right it's unbounded, but it is asymmetric. If you do a little smart math, you can parameterize it in a way which is a little simpler for everyday people to understand. And I suggest that you do that with your distributions. And it is often a very good approximation of reality. So all I'm saying here is don't just use a triangular distribution. If a distribution is unbounded, you're going to have to supply as a parameter bounds on the distribution. Spend some time parameterizing it in a better way if need be, and you will save yourself some trouble. Your simulation will be a lot better for it. Okay, the cumulating effect of agents' efficiency on queue time. I've sort of mentioned this when I was talking about how errors accumulate when you're in a queue. Now, I found this with our drive-through simulation. If I allowed the people who deliver food to the cars to be, I had a choice. So they could either be fairly intelligent or they could be sort of lazy and they could be lazy and wait for the cars to come to them, or they could be fairly intelligent and work out, oh, I can cross the lane here before that car arrives, and I can drive up to that car as it comes, and then I can follow it down, taking the order as I do. So for each car, small efficiency, but because it was in a queue, these efficiencies mattered, and they had a quite significant effect. So be aware that long queues and efficiencies can have a big effect on the results from your simulation. Okay, finally, anticipate the need to use multiprocessing. Simulation really can crunch your computer. It can pretty much brick a computer. So right from the get-go, code things so that you're at least building for the possibility that you're going to need multi-threading, okay? Multiprocessing. So typically you'll either run each agent, each car, each customer or whatever on its own thread, or the way that I do it is I run each simulation on its own thread. The threads all return their results, I pull them together, and I get my final result. Okay.
Are you using a CPU or a GPU?
Oh, I don't know. I can't remember.
Okay.
I just use a Python package for it.
CPU.
CPU.
Yeah. We haven't done any GPU simulations, but I'd love to try.
Okay. Yeah. Look, but I've seen speed ups of 75% or more. It's important. All right. Well, those are my tips. I have made. Over the years of doing simulation, I've made some dumb mistakes, so I hope you won't make these mistakes. So
I found it interesting how frequently you refer to spreadsheets. And so, in my mind, as we were doing this presentation, I viewed your spreadsheet as only the input into what you were doing. Is that correct?
that's correct, yes. Well, it's one of the inputs, yeah.
And so, are you taking the spreadsheet as an input and putting it into Python, or are you using another technology?
Yes, that's what I'm doing, yeah. Oh, I should mention, sorry, that is something I wanted to mention. Why would I use Python? C++ is a much faster language. Why would I use Python? I think Python is good for this, and the reason is because I believe what you should be doing is you should be building a class which is your base simulator class, which reads in that spreadsheet, but you need to supply those bespoke methods for it to call. So the way to do that is to inherit from that base simulation class Now, in order for that, for this method of doing things to be accessible to ordinary, to non-programmers basically, it needs to be in a fairly simple language, and I think Python is a good choice. Thank you. Any questions?
You've talked a lot about I assume a fast food restaurant simulation. What other simulations do you work with? What's the most common type of simulation?
Well, I do a lot of my work is for. Let me just run one, by the way. This is a more tricked up one.
While you're running this, can you tell us sort of what the different numbers and dots mean, or is that proprietary? But just so, how would you explain it, I guess, to a non-analytical person? I might be the only one in the room that's not analytical, but.
No, it's a fair question. I'll make them go. They're currently in the warm-up period, hence the grey. Oh, look, there we go. There's a car coming in. Have I stopped it? Okay. The white lines are just. I think the first one is needs to do ordering. Second one is it needs to do payment, and I think if it needs to do cash payment, it's black. The third one is pickup. It needs to pick up its meal. Now, it's been a while since I've done this one. These countdowns are for the time it's spending interacting with the worker. This blue dot on the top indicates that the food is now ready. And yeah, that's basically.
Okay, so you can see the food is ready before the card gets around to pick it up.
Correct.
Okay.
And what is the color of the car?
The color of the car. Red is a car that is not allowed yet to leave this section because it hasn't finished the tasks it has been assigned to do in that section. Yellow is it's interacting. Green is it's ready to go. Yes. Sorry. Was there a question before that? There was
Yeah,
something?
I'm sorry.
No, you were perfectly good. I was questioning, so we're looking at, I believe, fast food simulation. What other simulations do you work with?
Right. Okay, so I've mentioned a fryer simulation. I'm currently working on a fleet delivery simulation. So, again, it's for fast food, but it's delivering from restaurants to customers in the area.
We talked a lot about this in the manufacturing space, just anywhere really that there's bottlenecks. So you can think of whether that's dishwashers or burners or ovens, industrial ovens, if you will. It would seem that this sort of processing, anyone who's in the operations management stage is dealing with bottlenecks, throughput, flow process. It feels like there's almost a direct one-to-one application of this.
Have you done anything in healthcare? Because healthcare, there's a lot of similarities here. The background in healthcare is you come in the ED, you need to be triaged, you need to be looked at by a physician, you need to be doing a plan, and so forth and so forth.
Absolutely.
Like moving through an ER department for sure. Look at ER department.
Yeah, okay.
Yeah.
It's very simple.
Yeah, it's complex, a lot more complex.
Well, the complexity and just the human body and all the different people involved, and it would be complex.
You mentioned logistics. I was actually thinking about logistics as you were giving your presentation. Can you talk a little bit more about what you're doing right now as it relates to logistics? Did I misunderstand what you said?
Yeah,
I thought you were talking about trucking.
Oh, right, yeah. Okay. Well, the fleet simulation that I'm currently working on, the question is it better to have restaurants, to have, say, 3 restaurants share a fleet of cars, or is it better for them to have their own fleet of cars? Okay. So the way that you simulate this is you have you start off by placing restaurants on an imaginary map, and you then have a radius around those restaurants of which is a reasonable delivery time. Okay, so it might be 10 minutes of drive time is the radius around the restaurant. And what you will do is you'll have 10 cars, or let's say 5 cars to share, 5 delivery cars. They'll have to go to a restaurant, wait for the food, maybe they pick up 1 or 2 orders, then they deliver them out to the customers. It's a bit of a complex routing problem actually, because there are so many ways that the deliveries can be done. Car A could, pick up only one order, or could pick up 2 orders. Car B could pick up both of the orders instead. There's a lot of, it's as you know, it's a classic problem in computer science, quite difficult. And yes, I'm going to be using animation for this because it really is the best way to convince people of our results. But yeah, that's the simulation project I'm currently working on, together with more work on the Scryer, and I'm also, as I said, I'm writing a better engine for simulation.
So I've seen the 2-lane drive-throughs. Can I expect to see a 3-lane drive-through coming soon?
No, this is
We're absolutely.
This is me just amping it, and it's all, yeah.
Did you get to where you are on your own, or did you go into a simulation company and start to learn this stuff?
Well, I did some simulation when I was in college, studying computer science, and yeah, I mean, it sounds crazy, but I used to write computer games when I was a kid, and that actually helped with this. Yeah, I just sort of learned myself.
This strikes me as so far off the beaten path. How did you get into this? What tools did you learn? What, if someone was interested in this, how would they start?
They might want to look into well, Python is a good language to, if you, especially if you're new to coding, Python is a good language, and you might want to start with PySim, which is a Python package. You also, because I think animation is so essential to all this, you need to learn to do this sort of stuff. Matplotlib is what I use, and then I chain it together with FFmpeg. If you've got more coding skills, you might want to try a faster language. Yeah, Java or C++.
That's the second time you mentioned speed, and you said that Python was slower than C++. Can you talk to us a little bit about speed?
I think Casey might be a better.
Generally, C++ and C in general are lower language, so they can get closer to the actual hardware itself. So you have a lot more control over memory and how you allocate the memory. The big thing with Python and why it's so good is it kind of handles all that stuff for you. So you don't have to do things like memory pointers and stuff like that. It just kind of handles all that. The limitations are when you're doing things like multi-threading and stuff like that, you have to approach that stuff in a much kind of different way. It's not uncommon for us to meet folks that almost use Python, myself included. I'm not a Python programmer. I use it in a more script-like function and then a higher-end coding language, and that's just because of the nature of kind of what I do is kind of data engineering, moving data around. I don't need a lot of that kind of stuff. It's like one stuff, but stuff like this, like Peter's talking about, actually being able to code that stuff. And there's ways to do it. There's packages, and I think what the really popular one is to really get it where your Python code will be converted to C++ or C and then run. I forget what Win or whatever it is. It's really popular. Where you can actually code it and it'll actually kind of transpose it to it for you. And you can use some of that stuff. Python can do some of that stuff. You got to just do a lot of working with the different threads and stuff like that. So it almost becomes harder with Python at that time when you're trying to really access all that compute like that. But to get started and kind of start working with coding and stuff like that and do a lot of even the stuff we do, Python's just great.
Any other questions?
What's the kind of lead time for how much with this particular, I mean, obviously I know who the client is, I know. How much time are you spending with SMEs and people to actually get this kind of institutional knowledge? Because I imagine that is so important, right? I don't know if Peter knows how long it takes a basket of fries at X shop to fry or not, all when you first start. So how much time did you have to spend going around and talking to folks? Or was it more you told the kind of people you're working through what information you needed and they went out and got it?
Well, fortunately, I've worked with some process engineers who really understood.
They love that stuff, right?
Yeah. They're all, I mean, and also they've generally, in college at the very least, done simulation before.
Oh, really?
Yeah.
Cool.
So, yeah, it can be quite a process, especially since you evolve the simulation over time, and sometimes the new requirements don't fit in with the way you've coded it. It can be quite a problem.
Was this a problem you solved for a specific location, or were you able to scale it across? Because I'm sure there's some variation between locations.
That's the thing. This simulation that you're looking at now is actually described by a single line in a spreadsheet. It's a single row in a spreadsheet. There's lots of other rows in that spreadsheet, and those rows describe completely different drive-throughs with completely different layouts. Sorry, not completely different, but they'll have a different number of lanes, a different number of car spots. They'll do different things in different sections, and the workers will do different things as well. Anything?
You want fries with that?
Very impressive, you've done a great job.
Yeah.
Good job.
Thank you very much.
Thank you.
I started packing up the food, but if anyone wants to take a plate to go, please do.
Was that wrong?
No, it's perfect. It's perfect. You did great. Now, if only I could figure it out. We'll figure it out later. Bummer.
I did want to give the both of you a little thank you. This is my, should I unpack that first? A little thank you award for saying, being a speaker. I do appreciate that. That one is yours, that one is yours.
Thank you very much.
I appreciate you guys coming out. If you didn't sign in, please sign in. I will, if you have your email address on there, I will add you to the BhamQuants newsletter. Alternatively, you can go to BhamQuants.com and sign up for that newsletter. That'd be fine as well. Next event is the second Wednesday in January. We're going to be back here. I don't have a topic yet, but that's the plan. We would normally do the first Wednesday. That's January 1, so forget it. So January 8th, we're going to come back to here. Thank you for showing up.
Thank you.